So here's our laboratory one. When you submit the laboratory, you'll click here. You're going to submit the laboratory memo. And this gives you more information to complete the laboratory. You're going to do, you've got data set 1, and there's data set 2, and then there's doing the video analysis. When I'm grading the laboratory, I'm looking for, did you perform the task? And did you perform all the tasks? Did you document your results and draw conclusions from your data? Sometimes Mother Nature's not fair. And we can do the experiment right, and Mother Nature goes, nanner, 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 I'm not playing right with you today. As long as you are making conclusions from your own data and you have provided me with that data, I am not counting off that Mother Nature wasn't fair. That's not where we are. I am looking for proper grammar, proper capitalization, because part of science is communication. And you guys are probably going to write more in my class than you think. You said, oh, it's a physics class, we're just going to crunch numbers. Nah, you get to write too, because that's part of science. Ask questions, use discussion boards to get help, and then make sure you properly reference your items. So those are things that I'm actually looking for in the data. So you do have places that you can go in here. I've made it so that you have more than one attempt to upload data, and then I'm hoping everything gets in here. And the data and the labs are going to typically be due on Sunday night, except for the last week. And then I'm hoping the last week we'll be done with labs before the last week, so we'll get most of those there. Short, sloppy.
So this is all.
Yeah, go ahead.
This is all the steps that we need.
These are all the things that need to be in the laboratory report, right?
Oh,
And I'm
okay.
going to we're going to go through it and show you on a step-by-step basis in just a sec.
Okay, thank you.
Yeah, this is just a kind of a checklist. Did I get everything done that I was supposed to? Okay. All right. And then these are typically going to be due at midnight. So that's what that looks like when you come in here. Here's the example for this first report as well. Here's the discussion board. So what you're doing is you're going to open up data set 1. And it's an Excel file. You'll need to download it so that you're actually working with the file. All right. And it's an Excel file, and it's got the general data for graphing. You will also have a second data set. I'm going to go ahead and download the second data set. And now I'm going to go ahead and click open our data set here. You'll have to enable editing. I'll make sure I have my other data set. Okay, and you'll have to enable editing. So the first thing that you're going to do is there are 3 sets of data. It's force versus mass, it's force versus velocity, and it's force versus position. And what you want to do is you want to look at, is there a correlation? So what you'll do is you'll graph the data. So what you do is you highlight your data. You're going to go into insert, and then you have your graphing tools. We're going to use our chart and we're going to use a scatter chart. So here's my scatter chart. And I've got force on this side and I've got position on this side. And I'm looking at that data and it looks like it's scattered all over heck in a handbasket. There's no correlation. I can't make any interpretation about how force is related to position from this data set. So I'm going to say, no, there's no correlation here. It doesn't, my data doesn't show a correlation. There's no correlation. So that would be that first graph. Well, now I'm going to look at force. Let's look at force versus mass. So I'm going to go over here and look at this data. And I'm going to go in, I'm going to insert, I'm going to put in my chart, and I'm going to hit a scatter plot. Oh, well, that's a little different. I'm getting a nice straight line. I can see that there's a nice straight line. So now I know there is a correlation, and I can go in and make an interpretation about this correlation. And one of the things I can do in Excel is I can highlight it, and then I will right click, and I can add a trend line. This is just like doing that curve fit in the video analysis tool. I can do my linear line here, and I can apply it, and I can display the equation on the chart. I can see my R squared to show how good of a straight line it is. And I come back and I can close this off, and I now have a correlation for my graph. So I can say something about force. We can say, if I've got a straight line, we can say force is directly proportional to mass, and we have a proportionality constant in our slope. So for these first three graphs, that's exactly what you're going to do. You're going to plot those three graphs. You're going to tell me if there's a correlation, and you're going to write a little paragraph in your laboratory report. Now, these two, because what we're going to do with our next lab, when we use the IO lab, we're going to try and match the motion of an object with what we see graphically in the data. So we're going to do a position versus time plot here. So we're going to do that. We're going to insert our graph. All right, there we go. We've got our graph. And then what I want you to do with this one, there's not a correlation. In this case, we're actually plotting actual movement. What I want you to do is describe the motion in words. So let's say this is an ant. All right. We've got an ant that's starting at a position of 5 meters. And it's going to walk forward, probably pick up speed until it gets to our point that's at 12 meters. Then it's going to stand still at 12 meters for about 3 seconds. Then it's going to go back to its starting point, and then it's going to go at a much faster pace till it hits 32 meters, stop, and then retreat. So you're going to describe that motion. You're going to give me a paragraph that's describing the motion that's being represented on this graph. And you've got 2 of those to do. So it gives you a little bit of practice. Okay, so you understand what to do with this first couple of data sets. All right, so we're not going to save it, let it go away. Now, this one, you can do it a couple of different ways. You've got 4 data sets here. You've got time, distance, and velocity. And what you're going to do is you're going to obtain some data and tell me which object it is. And here's a table of known objects. So I'm going to do this a little simply. I'm going to take my time. I'm going to take this data set. I'm gonna copy my data set there. There's my time. I'm gonna get my velocity. And I'm gonna paste it special. I'm gonna paste it with the numbers. All right. Now we're gonna do a plot. So here I've got a graph. I'm not moving what I want to move. So I have a nice graph here. I'm going to go in and I'm going to add a trend line because we have a nice linear trend line. I'm going to plot my equation on the chart with my R squared value, and it'll pop up here. And now I have y is equal to 1.3x with an intercept. What we're going to learn is that there's an equation of motion where y will represent velocity. And so I can change that y to velocity. I can change that x to time. So now I have an equation that says v is equal to 1.3 times time minus my intercept, or that initial velocity. So I can compare this with an equation of motion. It turns out that 1.3 is going to be an acceleration. So by graphing this data, I can read the acceleration right off the graph. And that's an acceleration due to gravity. And we're going to see that over the next few classes. We're going to get a good understanding of that. But right now, if you know that that's acceleration, that 1.3, I can go over here and I can compare it with my known data. And it says Titan is 1.36. Well, if I know these data sets are real and I'm comparing it with what I have here, I'm going to say that that data set represents Titan because I measured it at 1.31 and Titan is 1.36. So this set of data is going to represent Titan. I want you to do that for each of these 4 data sets. You can also do a position versus time plot and do the same thing, but your model equation is a little different. And I'll show you that here in just a second, what that model equation would be. So you can do both, you can do it either way, but I want you to tell me what those 4 data sets represent based on these known values. So you're going to do the graphs, determine the data sets, and then bring it forward there. So that's what you're doing with this set of data. Questions? All right. So going back and just as a review of what you're doing. So we go here. So you're gonna, you've got this video plus the video on the data analysis. You also have this explained a couple of different ways. Maybe what I explained to you tonight is a little confusing, but those other 2 introductory videos are doing the same thing. You're gonna open up the data set 1 and you're gonna do those 5 plots. The first 3 you're gonna see is there a correlation or not. The next 2 you're going to look at, where's my description of how that thing is moving. Data set 2, you're doing the 4 different graphs and you're trying to determine which celestial object it represents. And then you're going to perform the video analysis, give me a screenshot so that I know you went through that. Write it up in a laboratory memorandum and submit it by midnight on Sunday. And I'm going to switch real quick. So now you should be able to see a piece of paper. So Taryn, can you see a piece of paper and give me a thumbs up because I can see you? See in my hand? Oh, I can't see it.
I can see it.
Okay,
I
great.
can see it.
All right, cool. Thanks. Okay, so as I was saying and describing it, if I have this was my velocity versus time plot, and we got a straight line. My straight line was represented by y is equal to mx plus b, and that's our algebraic understanding of what a straight line is. But let's talk about what this really means in terms of a velocity, and I'm going to go ahead and write out the words so everybody knows what it is when they're taking notes. This is a velocity time graph, and our velocity is in meters per second, and our time is in seconds. So I can rewrite this equation based on this graph, that this is now velocity is equal to some slope, because that's our slope, times time plus my initial velocity. That would be my y-intercept, and the y-intercept is the value at 0. Well, in this case, my 0 is time is equal to 0. So this would be my initial velocity. So now I can actually model my behavior. So velocity is going to equal some slope times time and plus an initial velocity. But let's look at what this slope has to be. And this gets us to our units. This has to be in meters per second. My time is in seconds. So the units of my slope have to be in meters per second squared in order to multiply this times seconds so that I end up with a value that's in meters per second. So if I've got meters per second squared, that turns out that that's going to be an acceleration. So now we can remodel this graph, this velocity versus time graph, as the velocity at some time is going to equal my acceleration. And this is going to be a constant acceleration, just because we know it's a straight line. It's represented by our slope, times time plus my initial velocity. And that 0 tells me it's an initial velocity. So now I've represented my graph into an actual kinematic equation. And we're going to see that kinematic equation in the next couple of lessons. We're going to get there. We're going to actually see that kinematic equation. So that's what you're actually graphing. So we're taking some data and we're actually going to give it physical meaning. So we're bringing back, we've done everybody a disservice, and that we have broken the math from the physics. And it really is the math and the physics are the same thing. And we're just shorthand writing what that information is. Well, it turns out if I do a position versus time graph, I'm going to get a curve. And so now I've got something that's a little different, right? I've got to have X is going to equal some initial velocity times time plus some constant here times time squared plus an initial position. because I've got to use a quadratic equation. So if I'm looking at this, I'm going to have y is equal to AT squared plus BT plus C. That's my good old parabolic representation. But we're going to change this that X or Y is going to be position. And we're going to represent that with an X. And this A is going to be some value times time squared. My B turns out to be my initial velocity times time plus my initial position. And it turns out that we're going to find out that that constant is actually acceleration divided by 2. So if I get this representation on the screen, if I take that value, multiply it by 2, I'm going to get the acceleration. And I can also use that model to determine which planet that I'm in. And again, I know that this is kind of out there, but this is going to make a lot more sense as we get to those acceleration and kinematic equations. So you can do the graph this way, or you could do the graph that way, but we wanted to start looking at our graphs in order to start making our tools better as we go through our E6 shortened semester.